So we have talked about shells and more shells, but today it's time to talk about things called subshells. So if we are given a photoelectron spectrum like this one, we see we have 4 peaks, which might lead us to say we've got 4 shells that contain electrons. But unfortunately, that's not true. But I thought I was getting this. Well, this shell, this peak, is pretty significantly different energy than the others. But these two, let me erase, these two are pretty similar in energy. As far as megajoules go, those are pretty similar in energy. And then this one is another one that's pretty different in energy. So we've got breaks along the x-axis that show us this first peak pretty significantly different from the middle two, and those middle two are significantly different from that last one. So what that really leads me to is to say this is shell 1, this is shell 2, and this is shell 3. We really only have 3 shells of electrons represented here. What? Yeah, hold on. Remember, this corner can be thought of as the nucleus, and those electrons that take 126 megajoules of energy to remove, those are closest to the nucleus. Then comes the electrons that take 9 megajoules to remove, then comes 5.31, then comes 0.74. So we're building out from the nucleus. My laser's not showing up there. We are building out from the nucleus. Uh-oh, PowerPoint's frozen. All right, got it back. So we're building out from the nucleus in shell. There we go, in shells. So, I know that the first shell holds 2 electrons. We've actually talked about that already. So 2 electrons are in my first shell. I'm going to call that shell n equals 1. We'll talk about why. My second shell has 2 electrons, sort of. This shell has 2 peaks in it. So it has 2 subshells. How do I know they should be called subshells? They're close in energy, relatively, close in energy. So these are indicating 2 different subshells of energy. So they're kind of the same distance, or pretty similar distances from the nucleus. So I'm going to put a shelf right above my 2 little electrons. I'm going to say this is n equals 1. Nope. I'm going to say this is n equals 2, and this is also n equals 2. But they're slightly different energetically. Remember, our ionization energy is the energy required to get up to the 0 line up there. So, if I total it up, we've actually already discovered that the second shell holds 8 electrons. So if 2 were already found in this first peak, it must mean there are 6 in the second peak. 1, 2, 3, 4, 5, 6. Yep. 6 electrons in the second peak. And finally, this is the same height as those other 2. That must be the shell n equals 3, and it has 2 electrons in it. So, because I know that this thing has 2, 4, 6, 8, 10, 12 electrons total, I can say this must be the electron spectrum of, you got to figure that one out. So what else can I do with this photoelectron spectrum? If I know that it takes 126 megajoules to remove an n equals 1 electron, I know the value of that energy level is negative 126 megajoules. I know the value of this energy level is negative 9.07. This one is negative 5.31. And this one is negative 0.74. So my energy shelves get, these top 2 are closer together than that one, and my scaling here is probably not great. Before I wrap up this pretty short video, subshells have names. We call the shells numbers, but subshells have names. And you may remember the name of them from long ago stuff. A subshell that can hold 2 electrons is called an S subshell. A subshell that can hold 2 electrons is called an S subshell. A subshell that can hold 2 electrons is called an S subshell. So those 3 green circled peaks are all S subshells. So as you increase the shell number, the first place electrons go are into the S subshell. So in shell 1, you fill the S. That's all there is. In shell 2, you fill the S first, and then you fill a subshell called the P subshell. A P subshell can hold up to 6 electrons. So this is my P subshell. So officially, we draw our spectrum, our energy diagram, like this, where I've got 2 little dots in the 1s, 2 little dots in the 2s subshell, 2 little dots, 2 little dots, 2 little dots. Oh, we're going to talk about that. Hold on. In the 2p subshell, and then 2 little dots in the 3s subshell. So why do I separate these out onto 3 little shells that are all the same energy? Well, we will continue to refine our definition, but I'm going to go ahead and say a few things anyway. This little shelf that can hold 2 electrons is called an orbital. And each orbital can only ever hold 2 electrons. So if you know P alone can hold 6 electrons, it must mean that P is composed of not 1, not 2, but 3 orbitals. So we've got shells, we've got subshells, and we will continue to talk about orbitals. S has 1 orbital, P has 3 orbitals. Isn't that fun? I think this is actually good enough. What? Yeah, I think this is actually good enough for us to refine our shell model and include subshells. All right, peace out, yo.